So we are live, you can start.
Okay, it has not yet started there in the YouTube.
There will be a 20-second delay. You
Yeah,
can
okay.
start, sir.
Yeah, it is. I'm just waiting for the YouTube link to work. Yeah, I think now it is working. Okay, so it will be. Okay, I have to read chat from that. Okay. Okay, welcome students to this live session of the Symmetry, Stereochemistry and Application course. And you are given some Google form to raise your questions, doubts, and I can see it only there are two questions. One is a question, and other one is related to a question in the assignment. And right now, I don't have the assignments with me, so I will check this answer if there was any problem in the assignment, and let you know through the email portal which you already are having and sending some questions, and we are trying to reply on a day-to-day basis. So the question that we have here is the order of stability of conformations of difluoroethane. So to answer that question, I need to draw a few things. So I will first share my screen with all of you, the entire screen, so that you can see what I am writing. And so as you can understand that the question says the conformations of difluoroethane, that means FCH2 CH2F. So simply it is like the molecule is like this. I'm drawing the corresponding Newman projection. Sorry, this is I'm drawing the Shawhorst projection, and from that we will draw the Newman projection of this molecule. So if you view the molecule from this side, taking this as C1 and the other one as C2, the Newman projection of this particular conformation would look like what I am drawing. So this is the fully eclipsed conformation, or the 0-degree conformation between the two fluorines. So now if you rotate the back fluorine by 60°, you will get the next conformation where the angle between the two fluorine is going to be 60°. Then again, when you rotate the back fluorine by 60°, you get the partially eclipsed conformation, which I am drawing now. Then again, if you rotate the back fluorine by another 60°, so this was 120°, you rotate it by another 60°, what you get is the anti conformation. So then this is the anti conformation or 180° conformation. And then when you again further rotate the back carbon by 60°, you will get the corresponding partially eclipsed conformation. So this comes at 240°. So another 60° rotation gives you the other Gauss conformation, which is equivalent in energy with the 60° position. And then another 60° rotation of the back carbon takes you to the original position. So if we number these conformers as 1, 2, 3, 4, 5 and 6, sorry, 5 and 6. So we can clearly understand that the conformer 1 has the highest energy because it is fully eclipsed. So fluorine atoms are highly electronegative, and there when one behind the other the repulsion is large. So one is the most unstable or most highly energetic conformation. Then comes these conformers 2 and 4. Okay, I think here there should be a fluorine. 2 and 4, which are the corresponding Gauss conformations, which are less in energy. But then again, when you go to 3 and 5, you see that they are in partially eclipsed conformation. So those two will have more uh, energy compared to 2 and 6. And then the last one is 4, which is the anti-conformation. And now you remember this anti-conformation, the fluorine atoms are totally 180° apart from each other. Whereas in case of these two Gauss conformations, the fluorine atoms are at 60°. So the CF bond, bond sigma bond repulsion will be more in case of 2 and 4 compared to 2 and 6 compared to 4. So 1 is highest energy, then 3, which is equal to 5 in energy, then comes 2, which is equal to or equivalent to, I would say, 6 in energy, and 4 is the lowest energy conformation. So if you try to draw the energy diagram for these conformers, it should be like this. 1 has highest energy at 0 degree, 2 has lower energy, quite low, and then has 3 which is higher energy, 4 has the lowest energy, 5 has similar energy like 3, and 6 has similar energy like 4. So this is 1, 2, 3, 4, 5 and 6. It goes back to 1. So this first question I hope is clear to all of you, that this should be the potential energy diagram for all these molecules. So for 1,2-difluoroethene. I could see there were some questions coming up in the YouTube chat window, but I'm not able to see those screens straight away. So let me first stop sharing the window and then I go back to the YouTube link if I can see the chat. So the first question that I have from Gautam Dutt. Sir, will you please discuss the phases of pyruvic acid? I think this was discussed in one of the lectures in the class. I will check once again, and if not discussed, then probably I will discuss this in one of the sessions that are not recorded yet. So I will explain this in one of those sessions. Again, there is some question related to the assignment which is shown as homotopic, but you are saying enantiotropic. Please write in email clearly that what you think is not correct in the assignment. We will look at that assignment together, because I don't have the assignment with me right now in this computer. Is there any other question? Somebody want to ask some question? Yeah, anti is more stable in case of this difluoroethene. Hope you can see the screen now. So now there is a doubt regarding the assignment of Pro R and Pro S. So let us try to answer that question. So Pro R and Pro S is assigned to centers which are going to be chiral, and at, when it becomes chiral, then this it is a R enantiomer or S enantiomer. So suppose we have CH3 CO C2H5 is this phase, and through a reaction you get a product by attack from this top this phase, so that the product that forms is this one, and if the attack happens from the other phase of this molecule, and you end up getting this particular product. Then depending on which one is R and which one is S, then these two phases can be identified as pro R and pro S. Similarly, in case of a compound maybe like this one, let us take one example. Uh, yeah, this is what becomes slightly difficult, because when you ask questions in advance, then I can think of the correct examples and then give you the answer straight away. But sometimes this when you ask the questions over chat, then it becomes difficult to find out the correct example. So maybe next time when you come for any live session, this type of live session, you please ask the question in advance, so that I can find out, I can have the correct example with me. But this example of pro R and pro S, I think, should help you to understand, right? So any other question? So any other question? So this form 2 that you have formed, the question that you have asked regarding the assignment 5, I will get back to you later. I have not checked this assignment yet. It says assignment 5 and question number 9. I will check that. So any other question? For this course that I'm running now, I'm not receiving a large number of question from the students in the Google Mail portal. So maybe people are able to follow the things, or I'm not getting actually any feedback how things are going. Do you have any question? Okay, somebody is asking, I have a doubt on attack of any one chair conformers. Can you please elaborate little bit? What is your doubt? Okay, so your problem is in case of substituted cyclohexane, how to identify the given pair is identical or enantiomer. See, this one, what you need to try to practice is to draw the cyclohexane chair form very carefully, and then apply the symmetry elements that may be present, whether there is a C2 axis or a sigma plane, and based on that you can say that whether it is it would exist as pure enantiomer, or it will exist as enantiomer, or it will be identical molecules. So the only way to understand is to draw the molecule yourself properly in the chair form, and then place the substitutions at correct places, and then try to identify what happens if you apply a mirror plane, and then draw the molecule and see whether they are superimposable or not. So there is no other way that one can try to understand this. Okay, so then the other question is, and other problem thing that you can do is you can make a model out of some ball and stick using some spherical object, and make a model of cyclohexane in chair form, and then try to take a mirror image and make another model, and then compare them whether they are identical or they are different. So there is one more question, and let us try to answer that. So somebody is asking, Ashish is asking, after attack of nucleophile on substituted cyclohexane, I'm not able to still understand, but then maybe if I try to answer, he may say something. Suppose this is my molecule, and I am trying to do a nucleophilic substitution using the base OMe. So now, if I am using OMe as base, it may be possible that it can go for SN1 reaction. Let us try to take a different base which will enforce the SN2 mechanism. Sorry, OMe will also go for SN2 mechanism, so no problem. MEO, methoxide, can attack from this side, and the bromine can go out, and it can give you a product which is this one. So if this methoxide attacks this first carbon, bromine is going out, and you only get the product where the OMe is anti with respect to the other bromine. Right? And if the methoxide attacks the other carbon from the back side, what you would get is this one. You can clearly understand that these two compounds are technically same, right? This is equatorial, this is axial. So di-equatorial and diaxial in case of 1,2 substitution is a trans compound. So we started with a cis compound and ended up getting a trans compound in this reaction, and this is the stereochemical preference of this SN2 reaction on either of those two compounds. Right? Now somebody is asking, in case of 1,4-OH substituted cyclohexane, why the boat conformation is preferred. You see, when you write 1,4-dihydroxycyclohexane, OH and OH, the corresponding boat conformation that you may think of is this one. So it is possible to have the intramolecular hydrogen bonding between the OH groups at 1,4 position, and that can lead to a better stability compared to the corresponding chair conformation. So the way I have drawn it may not look very clear, but what I can show you by hand is that the two oxygen atoms are close, and then the corresponding two hydrogens are like this. So if this is the oxygen of the boat, let me close this sharing so that you can see my video complete. That suppose if this joint is my oxygen and that end is hydrogen, this joint is oxygen and that end is hydrogen. So this orientation, which is like that, gives you hydrogen bonding between this hydrogen and oxygen, hydrogen bonding between this hydrogen and oxygen. So this will then give you the corresponding OH or hydrogen bonded structure, and that hydrogen bonded structure will have more stability compared to the situation where the anti-OH or the two trans OH up and down will be far apart and they will not form any hydrogen bond. So intramolecular hydrogen bond in 1,4-dihydroxycyclohexane gives you better stability, and that conformation is more stable because of hydrogen bond, intramolecular hydrogen bond. Yeah, somebody is saying the axial attack is more favorable than equatorial. Yes, it is true that axial attack is more favorable, and but what I meant is that by having those two different attacks, you get the same compound. Starting from a cis compound, you end up in a trans compound. Any other question? Yeah, it means two hydrogen bonds. So is there any other question, or should we close the session? Those who are online, are you going to write the final exam and you are going to use the grade for your course that you are registered, or you are doing it as an audit? Okay, so what is your doubt in the Falcon and ANH model? Okay, what is Falcon and model? You see, you are actually going little fast, because this will come in week 9, and currently you are at week 6, I think, right? So in the ninth week lecture, you will have dynamic stereochemistry aspects. So there I will be discussing about stereospecificity and stereoselectivity in organic reactions. So there we will talk about Cramp's rule and Falkenhayn model and its applications. Okay. Any other question? Okay. So thank you. It was nice interacting with you like this. Do send me the questions through the discussion forum portal, and me and my teaching assistant Lavini Singla, we try to give answers on a weekly basis. And there are some doubts which have been raised regarding the assignment, so we will check those together. and if the assignment has already been graded and we find there is some issue, then we will try to address that while tabulating the final marks. Okay, so thank you. Bye.